All right. So as many of you know, there's a strike ongoing that most of our psychology colleagues are partial to, which is probably why we see fewer faces today. I'm not partaking in that because I'm a postdoc salary, you can't. But I thought as my little act of civil disobedience, I would tell you how to hack your pupillometry study. We're specifically going to talk about how to mess up your science in a way that benefits you. And a lot of this has been said on how p-hacking influences science, and as Camilla nicely illustrates it, there's really elegant methods to pick up on power failures in the field. So what you really want to do is get ahead of that P curve essentially, and do the hacking not in your statistics but in your actual methodology. So what you really want to do is set up your methodology in such a way that your outcome statistics will look beautiful and clean. So that's what we're going to do today, and we're going to do.
Just remember the talk will be recorded.
Yes. So for those of you looking on YouTube right now, all 5 of you, sorry. So the idea is essentially that we're going to do this in the context of pupillometry because it's a really cool and hip method that after a brief surge in the 60s and 70s has made this reappearance and is now connected to literally every single cognitive thing you can find. Is visual attention, visual short-term memory, working memory load, or a cognitive load in general, to imagination, several different aspects in language. Basically, you can think of any cognitive metric, and there's probably a pupil equivalent of it. So before we go into that, I'll just show you how we compute this method. So this is a video. Just keep looking at it because at some point the pupil will increase a bit when the rodent in question gets the reward, and I'll just talk over it. So focus your eyes there. The idea is essentially that we have an eye, which you can see in the top left. That's the OG frame. There's this kind of bright spot in there. That's what we call a corneal reflection. And there's this dark spot in there. That's what we call a pupil. You might notice the lack of eye white. That's because it's a rodent rather than a human. I thought I'd switch my examples up a bit. This is some hacked together pupillometry toolbox that I wrote for specifically this. But the bottom line is that we get some kind of estimate of how big this rodent's pupil is. You see it shift up and down a bit. That's because it's running on a little treadmill. Just ignore that. The bottom line is that we can get a metric of how big the pupil is, and we can relate that to events in the actual experiment. For those of you who like humans better than rats, I have this nice data set of babies that my collaborators work with, and I thought that was a really impressive early thing. And then it turns out that this guy, also with one of the best names ever to be in neuroscience, Enzo Monica Hall, published in some kind of weird small Elsevier journal, what should have arguably been in Nature, pupillometry in utero. So this is basically using echoes to get at the eye of a fetus, actually quite a large group of fetuses, and as you can see, there's a little pupil over there. So you can do eye tracking, or at least pupillometry, even before your participants are born, which I find is a really nice human example as well. Anyway, so if you do this in your lab, or in 2 of the examples I just showed, what you get is this kind of signal. This is particularly nice signals from an eye link with somebody in the chin rest. This is also me, so I'm an ideal eye tracking participant. I only blink when I'm supposed to blink, and I don't really do other stuff that isn't in line with my experiments. Another pro tip for hacking your experiments: be your own participant and invite your colleagues to do that as well. So the idea is on the y-axis here, we have some kind of arbitrary amounts of units for the pupil size. So this can be the amount of pixels in the image, or you convert it to millimeters if you have a kind of standard eye that you're anchoring to. But in general, this is the optical image that you take from your video stream that has the pupil in there. There's a certain event that sets on at somewhere here, and then we see this decrease in our signal, and then we see this weird little bloobly bloop here. That's the official scientific term within pupillometry for these kind of things. And the idea is that this is a blink, but you would see very similar things if people make other eye movements. So you want to get rid of that, we want to smooth that over. So what you can do is take the velocity profile of this particular trait, so take the first derivative. Pupils are very slow, so that should end up about 0-ish. So that's the trace. So that's a normal kind of range of changes over time. And then here we see these rapid decreases and then another rapid increase as well. So basically, there's a pretty easy hallmark in the first derivative that allows you to get at these blinks and saccades. So you get your time points of that, and then what you can do is use those two starting and ending time points, usually with a bit of a buffer, because then you get the start and the end of the eye movement as well. You take another few points so that you can do cubic spline interpolation, which is kind of a non-linear way of doing these things, because oftentimes the signal isn't linear in the places where it's gone, and then you can basically draw a line. It's not quite clear in the slide, but there's now a line drawn in there via cubic spline. Sometimes that doesn't quite work because you have too few points to do that kind of interpolation. Sometimes it doesn't quite work because the signal isn't quite as nice before and after, so you get a weird over-exaggeration. You can also just use a linear interpolation if you're scared of that. So that's our basic signal, and now let's go on to the meaty stuff. How do I get a really cool pupil effect that I can then use in my paper to give it that wee bit of extra that I need to get in a slightly higher impact journal than if I only had behavioral data? So one thing that triggers pupils a lot, which is arguably their purpose, is light. So what we see here is at the green bar, that's the onset of a screen that goes either from white to black or from black to white. So basically minimal luminance to maximal luminance or maximal luminance to minimal luminance. The blue trace is the trace that you see when you go from white to black. So you get an increase in the pupil size because now there's suddenly less luminance that is causing it to constrict. The yellow trace is for the reverse. So basically, you see an onset of this massive bright stimulus, and therefore your pupil constricts. This is about a 40% increase, or about a 40% decrease, which dwarfs everything in all cognitive effects that you can see in pupillometry in general. Those are like percentage, maybe 2%. So this is like a really, really big thing. So if you have a really small imbalance in the luminance of your stimuli, you basically have a similar effect that you would have if you were to have an actual cognitive effect of the difference between those two stimuli. So pro tip number one, imbalanced luminance in your stimuli that is systematic across your design will cause you to have effects across your design for those two stimuli that will look like an actual effect, but actually are caused by luminance. If you get a stickler of a reviewer that is aware of this equiluminance kind of thing, you can also use sounds. And I swear there's a really nice paper that uses a nice intensity of sounds and that different intensity showing different pupillometry effects. That's quite recent and has beautiful figures. Can't for the life of me find it. So instead I'll give you really old papers. On the axis here we have an increasing and then decreasing sound level in a stimulus presentation. On the y-axis we have pupil size. So basically, with an increase of the sound, we see an increase in pupil size and then a decrease again. And I find another small paper from the 1980s, and this is actually Chris Frith, who is better known from being Uta Frith's husband. And he shows very much the same thing. So we have one noise on the left and another noise on the right. The white traces are the traces that a continuous sound was played. At 0, there's an onset of a flash. So basically, we see that the pupillary response to the flash is to shrink, but that shrink is exaggerated in silence compared to noise. So if you want to kind of play around with that a bit, not using differences in stimulus intensity that are visual but auditory instead works beautifully as well. So if you want to cause some systematic differences in auditory stimulation, for example, in a feedback sound that you play after a reward is given, if the feedback for the positive reward is a lot more intense than the feedback for the lack of reward, then you get this really nice effect in the pupil that seems like a reward effect, but really is down to your intensity. So pro tip number 2. Another thing is that eye movements can change pupil size. So it's not just those distortions that we saw earlier in the basic trace, it's pronounced effects after the eye movement on the pupil. If your pupil moves, you get this little wiggle, and that's something you can use to your advantage as well. So this is a really brilliant paper, partly because what they do is present do's and don'ts in pupillometry that are, for those stickler, proper scientists. But what we can take from that is also what effects work quite nicely if we want to game our methods. I highly recommend reading this if you're actually interested in pupillometry. Right? So what they did is a really interesting design for different conditions here. We're going to ignore all of them, but the bottom line is that there is a chaotic kind of condition on the bottom versus a regular condition on the top in terms of timing, and then there's identity differences between them as well. But we're going to ignore all of that because what they regressed out is that effect compared to this effect. And this effect is of two different types of eye movements, which people were making throughout this experiment. The green curve is if a blink onsets at 0, we see a decrease in pupil size and then an increase in pupil size again. And this is about a 20, actually quite steeper than that, 80% decrease here, but it's z-scored, so don't interpret that as actual percentages. And after a saccade in black, which is a rapid eye movement from one place to the next, we see a similar dip and then a return again. So what we learn from this is that blinks have pretty pronounced effects. And what we know, if we know a bit about blinks, is that blinks occur for different conditions at different times. So there's a bit of a contentious but reasonably emerging trend that higher levels of dopamine also increase your blink rate. So if you are in a condition where, or at least in an experiment where you manipulate those kind of conditions, your pupil is basically going to already be affected by the increased blink rate. So you have two metrics for the price of one, which is really, really cool. To quantify this a bit more, so this is the fraction of total explained variance on the actual pupil trace of, this is an experimental condition, high-low, doesn't really matter what those actually mean. The problem is that, or at least the advantage for us, is that blinks and saccades on the right dwarf the effects of this particular condition. So if you imbalance your conditions a wee bit, in terms of the amount of blinking that people do and the amount of saccading that people do, that's great for your future pupillometry output. Another bonus thing from this paper, so over the x-axis here we have trials. In the green experiment, the trials were slightly longer than the red experiment, so it looks like it's a steeper line, but it's actually not. These trials were about 3 seconds, these trials were at 5 seconds, so in reality the slopes align much closer. But the bottom line is that we go from pretty big pupils to pretty small pupils because people just get bored. That's what happens in all of your experiments. So if you're trying to do something like, investigating cognitive fatigue, that's a really nice signal to go for because it increases over your experiment, and also general fatigue just increases. So you can't really differentiate the two. So you can make a really strong claim about cognitive fatigue being reflected in the pupil, which is really, really cool. Just so you know, the different lines you see over superimposed are the different types of conditions, so there isn't really an effect of that over this fatigue. So it's really just a general kind of fatiguing element in there. So my last point is actually a very basic methodological point. Most of the eye tracking that we do is video-based eye tracking. So we have a camera, it's pointed at a participant, usually from a particular angle. So if I move my pupil up, my camera is going to see less of that pupil because the eye is a sphere, so it kind of disappears towards the top half of the sphere. So that's a very kind of theoretical thing. These people have actually measured the effect on your pupil size from gaze estimation. So imagine that this is the entire screen, one of those blocks. In the middle, we have the middle of the screen where we normalize pupil to 1. And then if we go to the eccentricities, and this is again purely because of that camera artifact, pupil size is radically different in the bottom right corner compared to the top left. So one thing we can learn from this is that if I present stimuli here versus here, there doesn't have to be a difference in the stimuli at all. There will be a difference in the pupil response to it, though. So that's a really nice way of, again, manipulating your own experiment to show nice data. This is kind of a generative model that these authors put forward that basically entails a model of the eye and the response to a camera to that. So what these sticklers say is, now you could subtract that generative model from your actual pupil size and therefore create a kind of homogeneous field that would correct for these kind of artifacts. But we're going to ignore that because this isn't a methods journal, so nobody will read this anyway. So your reviewers are not likely to be aware of this. So you can get away with not doing it. So in conclusion, what you want to do to game your paper is you want to use stimuli of different brightnesses or loudnesses between different conditions. That's really important. There need to be systematic differences between these things that co-vary with your conditions in your experiments. You also want to force participants to make many saccades or blink more in conditions that you think a pupil should be larger in, or smaller perhaps, depending on where your effect is supposedly early or late on. And also you want to present stimuli at different eccentricities on your screen so that you can really optimize that differentiation that you see over the screen. So for example, this could be a roving bandit task, and my one bandit is super luminant compared to the other bandit. Also, it's closer, so it's going to create a larger pupil anyway. So there's also such a thing as cortical magnification, by the way, going on here. So the closer your stimulus is to your fixation, if these were completely optimized for equiluminance, which is something you could do to appease like reviewers that are a bit more on the methods, then you could still basically make it so that the cortical magnification of this one is a lot larger than of this one. So you could still be getting away with your pupil effect, even after correcting for all of the things I just mentioned. If you want another example, this is actually a really nice paper. So I'm not going to name the authors, and there's a bunch of other stuff in this paper that is actually really cool, and the authors themselves are also just lovely people, which has nothing to do with their science, but I didn't want to shame them, especially because apparently we're being recorded. But one of the things that they do, and of course this is in PNAS, but one of the things that they do is they have this really cool manipulation of a pupil that in a decision-making task where you need to invest as a participant into an agent, they make that person's pupil a bit smaller, like normal, or a bit bigger. And the idea here is that you're supposedly seeing pupil mimicry. That is a social effect that essentially means that if I see a large pupil, I'm going to increase my pupil and buddy up to this participant. So basically, these people find a really nice effect of that. The blue curve is the dilating agent curve. And in response to that, people do indeed increase their pupil size. So we can now say, oh, this is a lovely social effect of pupil mimicry. And of course, there's these sticklers for rules that say, oh, pupil mimicry is actually just a result of brightness perception because a larger pupil decreases the eye-wise and therefore changes the luminance of your stimulus to a slightly darker stimulus. And of course, to a slightly darker stimulus, you're going to see this increase in pupil size. But these people are in Journal of Cognition or something. So, and got a letter into PNAS, but this is a letter of one page. So nobody's really going to read that. Your original paper still stands and is widely cited in your field, which is great because that's what we're all after. This is just to confirm that if you actually equalize those eye movements, you don't see a difference at all between small, middle, or large pupils. So there's a profound number of null effects. So this is all super boring proper science that we're not going to look at today. If any of you have any questions on how to extra game it, I'm all yours. Thank you very much for listening.